Hello, my name is Patrik, and this is work done together with Kucherenko, Gustav, Henter, and Jonas Beskow. And we're all from KTH, the Royal Institute of Technology in Stockholm, Sweden. The title of this work is Let's Face It. And what we've been working on is a probabilistic multimodal interlocutor-aware system for generating facial gestures in dyadic settings. And what I mean by facial gestures is both head movements and facial expressions. A lot of prior work have been looking at speech acoustic-driven facial generation. That is, we feed a model with speech acoustics and out comes, well, in this case of Karas et al., vertices in order to create a 3D model of a face. Another example is text-driven models, like this one by Chu et al., where text is fed into the model and facial gestures are generated. But one key component is missing from these works, and that's the interlocutor. It's very important that the social robot or virtual agent is taking the interlocutor into consideration when generating a response. Like, for example, the facial expressions or the speech from the interlocutor as part of the facial gestures that the agent is generating. We are, however, not first doing this. Ahuya et al., for example, created the system which uses multimodal input, both speech and upper body gestures, in order to generate agent gesturing. And they could also control how much dyadic versus monadic behavior the agent would have. However, this is slightly a different problem, since they are tackling the problem of upper body gestures as opposed to facial gestures. And their method is also not probabilistic. However, a probabilistic method that has been introduced is Dyadic by Huang and Khan. However, this method is unimodal. They only use pictures of an interlocutor in order to generate pictures of, well, not an agent in this case, but the person. However, these pictures are not really usable for controlling virtual agents or social robots. Similarly, another similar work is by Feng et al. They have a unimodal input, that is facial landmarks into the model and facial landmarks out from the model. It's semi-probabilistic in a way that they do train a variational autoencoder, but they do not sample from it during synthesis time. And as I said, it uses facial landmarks, which is similar to Dyadic, not entirely helpful for controlling a virtual agent or a social robot. We, on the other hand, use flame parameters, which are highly expressive parameters in a low-dimensional space, where we can control the facial expressions. This lets us, together with our synthesis pipeline, which I will explain to you in just a bit, be able to also disentangle the lip sync from the rest of the facial expressions. And now I'll show you an example of our method. You will see two avatars interacting. You have the interlocutor on the left and the generated behavior on the right. Please note how a smile in the left avatar triggers a smile on the right one. These avatars are rendered using a synthesis pipeline, and the facial gestures for the interlocutor are extracted from a real person. So, our method. As I said, we use a probabilistic approach. More precisely, we use normalizing flows. Normalizing flows are steps of nonlinear invertible transformations where we can transform, in our case, a standard Gaussian distribution through a so-called steps of flow into a more complex distribution. This has been shown to work quite well in Moglo, where Henter et al., for example, managed to generate character locomotion. This has further been used by Alexandersson et al., where they extended Moglo to be able to take speech and style control parameters in order to generate style controllable upper body gesture generation. So it has been shown that this kind of method works quite well for generating upper body gestures. Therefore, we thought that it can work quite well for generating facial gestures. And since our method is probabilistic, we are able to generate very different plausible motions for the generated behavior. As you can see, the left side is the same in all of them, but the right side differs. Our method is, as well as I said, multimodal interlocutor aware. This means we take the speech and facial features from the interlocutor as inputs to our model. So, the system architecture. As I said before, we have both features from the interlocutor and the agent. On the interlocutor side, we have facial features, the flame parameters as I described earlier, and speech acoustics, MFCCs. And these are passed through separate modality encoders, basically RNNs. Then on the agent side, we have the previous facial features and speech acoustics again, MFCCs, also passed through our modality encoders. This is then concatenated and passed as conditioning for each step of the flow. And the normalizing flow will then output a distribution of plausible next poses. We then sample from this, and we will then feed this in an autoregressive fashion as input to the model as previous time steps. So, our synthesis pipeline. We used Voca in order to create the lip sync. This was done so we could separately control the lip sync and the facial expressions of the agent. We also created a crosstalk canceling VAD mask that we multiplied with the Voca output because we only wanted the lip sync where actually somebody was talking. This was combined with our model output and then in turn passed to the rendering engine in order to create the 3D face. As for the data, we used the ManHub mimicry database. This database was annotated for various forms of mimicry, such as smile, head shakes, posture mimicry, etc. From this, we took mimicry segments that were annotated for smile, nods, and laughters. We also took non-mimicry segments, which were unannotated segments. And here's an example of the database, and also the result of the output from our synthesis pipeline.
It was I felt like I was there for like 2 months. I had this guy's hassling.
Okay, so we wanted to see, does our system actually work? So we performed an evaluation. For our first experiment, we asked the question, can participants tell the difference between ground truth and mismatched facial gestures? And what I mean by this is, we showed them clips with 2 avatars, as you saw before. The left one was the interlocutor and was always the same, but the right side was either the ground truth, facial gestures, or it was facial gestures from another point in time. We were wondering, do people even notice the difference if we would take facial gestures from another point in time? For our second experiment, we asked, can participants tell the difference when the model is given the ground truth versus mismatched interlocutor features? And this, similarly to the previous experiment, we showed them videos of the interlocutor on the left side, but the generated motion on the right side. However, the difference was that either the generated behavior was based on the interlocutor facial features and speech features, or it was based on interlocutor face features and speech features from another point in time. And the question then was, could they see this? The third experiment, how does the model perform without facial features from the interlocutor? We basically wanted to know, if we remove the facial features from the interlocutor, will the model perform better or worse? And similarly, what happens if we remove the speech features? We also ran additional experiments, but those are covered in the paper. So let's talk about study design. We had 30 participants per experiment recruited from Amazon Mechanical Turk. The question we asked in all of the experiments was, which of the 2 characters on the right side of each video has the most appropriate behavior in response to the character on its left? All clips were evaluated side by side. That is, on each page, we showed 2 videos, and each video contained 2 avatars. And the participant could choose which one they thought was more appropriate. Also, they could say just that they thought that both were equally appropriate. We used binomial sign tests with Bonferroni corrections for all of the experiments. So in our first experiment, where we asked, can participants tell the difference between the ground truth and mismatched facial gestures, we saw that there was a difference between the so-called mimicry segments and non-mimicry segments. We used 34 mimicry segments and 30 non-mimicry segments. And the participants significantly preferred the ground truth over the mismatched videos in the mimicry segments, while in the non-mimicry segments, there was no significant difference. We think that in the mimicry segments, the interlocutor awareness was actually of importance and much more salient than in the non-mimicry segments. So for the rest of the experiments, we decided to not use the non-mimicry segments and only look at the mimicry segments. So for a second experiment, we asked, can participants tell the difference between when the model is given the ground truth versus mismatched interlocutor features? And the answer was that yes. And they did prefer when the model was given the interlocutor features, the correct interlocutor features, rather than the mismatched ones. And this seems to indicate that the model leverages the interlocutor features properly, just like a human does when taking what the interlocutor says into account when doing their facial gestures. In our third experiment, how does the model perform without facial features from the interlocutor? Well, here we see that this had a negative effect on the appropriateness. And this seems to indicate that the facial features is quite important to the model. Looking at the speech features, however, we see that there was a significant positive effect of leaving out the speech features. That is, that the speech features seems to be less important than the facial features. This might also have to do with the parameterization of the speech features. We used MFCCs in this case, but it would be interesting to try out different parameterizations instead. Let's talk about limitations. One limitation was that we didn't have any sound in the evaluated clips. This was based on a pre-study that we did that showed that the participant paid a lot of attention to the semantics and the connection between the semantics and the facial gestures. And since our model is not trying to model the semantics, we thought that it was best to leave this out. We also reran experiment 2 with audio, and we got the same results, however, with a less stronger effect. Another limitation is that the clips that we showed were relatively short. They were on average 3 seconds with standard deviation of 2, but up to 8 seconds length. This was due to the fact that we used the annotated mimicry segments, and they had a certain length, and we didn't want them to be overlapping, so we just used the length they were at. So in conclusion, we have presented a model which is able to generate interlocutor-aware motions. And our experiments also show that the facial features seems to be the most important input to the model. Future work should also look at comparing the system to other systems and further explore different ways of encoding the different modalities. I would like to thank my great co-authors, Kucherenko, Gustav, Henter, and Jonas Beskow. Now we can take any questions. And all the code, the facial features, and video samples are available on our project website. Thank you for listening.